Let's now summarize the different methods of the synthesis of the aryl halides. Aryl halides, we get it by the direct halogenation of the benzene ring. You have a benzene and we can replace a hydrogen atom from the benzene by direct halogenation. Like suppose you will react with a chlorine molecule, and we use here the Lewis acids. The most commonly we use is a AlCl3 as a catalyst, right? And Lewis acid, we can basically use any Lewis acid here, and it is the Lewis acid that helps us here to generate a Cl positive, the electrophile from the chlorine molecule, right? So it's because of this AlCl3, the Lewis acid, that can help us to generate the Cl positive from the chlorine molecule. And it is this electrophile that attacks at one of the positions on the benzene ring and replaces the hydrogen there. And what you get then? You get a chlorobenzene, right? So you get a chlorobenzene and you get then hydrochloric acid. So this is one method of getting the aryl halides by the direct halogenation of the benzene ring. Chlorobenzene, again, if you try to further react with another molecule of chlorine, so then now this chlorination will occur at the ortho and the para positions only, right? So it will occur at these two positions. These are the ortho positions and this one is the para positions. So if you further do the chlorination, right, if you do the further chlorination on the chlorobenzene, then what do you get? Again, we use the Lewis acid as a catalyst. You get a dichloro product, but now the chlorination will occur at the ortho position and the chlorination will occur at the para positions. Alright, so it's gonna be the here. Now these are the two positions at which the electrophile that will be generated from the Cl2 is this electrophile. It will attack on the ortho and the para positions on this one, and so that's why you get the two products. But since the ortho one is less stable than the para one, and the para one there is more stability. Why it is more stable? Because here we have the chlorine atoms away from each other, the static hindrance is less, so that's why this is a major product. While as at the ortho positions there is more repulsion, more static hindrance, so this will be the minor product here. Alright. The further chlorination only occurs at the ortho and the para because the chlorine is an ortho-para directing group, right? The chlorine is an ortho-para directing group. It has low pair of electrons, and due to the resonance now, electron density will increase at the ortho and the para positions. So that's why the second chlorine molecule, second chlorine ion, is going to attack at the ortho and the para positions. So chlorine, being ortho-para directive group, will attack, will direct to the electrophile to attack at the ortho and the para positions. So that's why you get the two products here. Okay. We can also get the aryl halides from the benzene diazoxide salts. So the second method of getting the aryl halides is reacting the benzene diazoxide salt molecule with the hydrochloric acid and the copper chloride. So here this nitrogen molecule is replaced as an N2, and what do you get? You get a chlorobenzene. You get here the chlorobenzene and you get the nitrogen there. The nitrogen atom, which is attached to the benzene, is actually positively charged atom. It does not have a lone pair of electron. That's why it's easy to replace this N2 from the benzene diazoxide salt directly by reacting with any of the these nucleophiles. Okay, so the reagent that we use here is the copper chloride and HCl, and this reaction is called as the Sandmeyer reaction, right? This is called as the Sandmeyer reaction. Okay, so in the Sandmeyer reaction, you get a chloro or the bromobenzene from the benzene diazoxide salts, right? If you use another reagent, suppose you're going to react with the same molecule with the copper and the HCl, right? We modify here the reagent only. Rather than copper chloride, if you take the copper and the HCl, you again get the same product, the chlorobenzene. Again, the nitrogen will be replaced as an N2, as a nitrogen gas here. The difference is that here we use the copper chloride and HCl, here we use the copper and the HCl. This is a modified form, and that's why this is called as a Gutterman reaction, right? This is basically a Gutterman reaction, and this Gutterman reaction has an advantage over the Sandmeyer reaction, that this is producing the more yield. You get a more yield here than the Sandmeyer reaction. Okay, so why we need this benzene diazoxide salt, and from which substance you get this benzene diazoxide salt? Normally, if you look at the aniline NH2 group which is attached to the benzene, we know that here in case of aniline, it is the nitrogen that has the lone pair electron, and that electron pair can undergo the resonance with the the pi electron system of the benzene ring. So that's why it's very difficult to remove this nitrogen here, NH2 group, from the ring. So substitution, nucleophilic, this substitution here is not possible in the NH2 molecule in the aniline. That's why we first convert this NH2, this aniline here, into the diazonium salt by reacting with the nitrous acid, okay, with the nitrous acid HNO2, and what do you get then? You get N2Cl negative, and it is this benzene diazonium salt from which you can get the further substitution, and you get the chloro or the bromobenzene. Okay, you can get from this benzene diazonium salt a variety of the compounds. You can even get the phenol that we will discuss in later in another video. You can even get the phenol if you react with the water, right? Because it's not easy to remove this nitrogen from the ring, with the nitrogen having a positive charge and it does not have a lone pair electron, so that means you can break this bond very easily now. Okay, and you can also react with the potassium iodide, and here the iodine will replace this N2 again, just like here in case of a chlorobenzene. You get now iodobenzene, and again here this nitrogen is replaced as an N2 group. Okay, so you just react with the potassium iodide, the iodine will replace it. Any nucleophile now can replace this N2 group, because nitrogen does not have a electron pair available that can undergo the resonance, right? So in aniline it's difficult to remove, very difficult to remove, right? Because of the resonance there, because of the double bond character between the carbon and the nitrogen there. So that's why we first convert the aniline into the diazonium salt. Right, so we use the nitrous acid, and one more interesting thing is this nitrous acid is highly unstable, and whenever we need this nitrous acid, we prepare it in situ, means we prepare it in the reaction mixture by reacting the sodium nitrite NaNO2 with the HCl, hydrochloric acid, right? And you get the nitrous acid. It is this sodium nitrite and the HCl that actually converts the aniline into the benzene diazonium salt. All right, so this is another method of getting this aryl halide, chlorobenzene or the bromobenzene or even the iodobenzene. Hope you got it. Thanks for watching the video. Bye for now.